impedance and admittance. Oh.
Which note set is this?
15.
15.
You guys don't have it?
No.
Oh. Woo. Victor has it. You guys should be like Victor.
I got 15, 16, and 17.
At 3 a.m. He's got it also.
Did we tell you?
Yeah, he said the whole thing was good, the whole chapter.
He told us
It was till
at
19.
Oh. Well, fortunately, there will be a video of this, so you can go back and get the notes. You didn't print it either? You did? Oh, Chase. Be like Chase and Victor.
And Will.
And Will.
Just leave me out of school.
But have hair. Nothing. Okay. Input, admittance, and impedance. Like us. Like us. Okay? I like it. It's cool.
15 through what?
15 through, I don't even know, 19 maybe?
Yeah.
Groovy post. All right. So, input, impedance and admittance. So this is chapter 14, 13, 14, 13? I don't know. Something like that. Pretty cool stuff. We get to do cool things where we can model. So where we're headed with this is we're going to get to model systems from the linear graph directly to a transfer function. Okay? No, you don't have to do any of the elemental equations, continuity equations, compatibility equations. You don't find the state model. You don't have to do any of that stuff. You can go directly to a transfer function. Pretty awesome. However, it's all underlying there too. So you could really it's sort of 6 or half a dozen. So it's kind of a shortcut in some cases. So it's kind of cool. And then next chapter we get to learn about what to do with transfer functions, which is cool. Are you guys as amped up as I am? I was up to like 2 a.m. preparing for today because I forgot that today was Engineering Awareness Day, which, by the way, sounds like a disease. But for whatever reason, that's what it's called. Cancer.
Because we stay up till 2.
Yeah.
Okay. We should stop joking about cancer. That can't be our inside joke in this class.
No. Yeah.
It's pretty terrible. It just did.
Speaking of impedance.
Speaking of impedance, thank you, Jordan. We here, I can't even read my own writing today. We here introduce a generalized version of the familiar impedance and admittance of electrical circuit analysis, in which system behavior can be expressed algebraically instead of differentially. So, remember when we did circuit analysis and I said, oh look, you can just use impedance and you don't even have to find a differential equation. Remember that? Mechatronics way back in the day? We're going to do essentially that again. So if you were tracking on that, like you're so good right now. Like this is going to be the same stuff. Okay, just a little bit more general. We begin with generalized input impedance. So input impedance is something that is associated with every element or system. And so let's draw something because drawing things are fun. So let's draw a system that looks like a peanut or potato, probably more like a potato. Probably more like that meme guy, like rah, I don't know, anyways. With like the big like the teeth. That guy? Anyways. Yeah, so here's our system. It's going to be hard to keep me on task today. System. And this system has a source that's linked up to it, okay? So I'm going to draw it like this. Ooh, the really big node there. That node is just a special large node. Okay, and this is a source. So it could be an across variable source or a through variable source. We're going to consider both possibilities. So whether it's an across variable source or a through variable source, it has an across variable that goes in, right? So I'm going to just draw like v in to be like across the source like this. And it's going to also have a through variable as well. So I'm just drawing generalized across, generalized through sources. So this source, you know, if it's an across variable source, it has v in specified, and then f in is whatever the system allows to flow in. If it's a through variable source, f in is specified, and then v in is whatever the system allows it to be. So now we have this picture. We have our potato. I'm from Idaho, so it's natural that I drew a potato. The ideal source specifies either v in or f in, right? So either we specify f in if it's a through variable source, or v in if it's an across variable source. And then the other one it depends on the system. For the input, vs equals v in of s e to the st, meaning that we have an across variable source. The resulting particular solution for the through variable, f in of s e to the st, is defined by the transfer function y of s. So here is that transfer function in the expression. So we have f in of s equals this transfer function y of s times v in of s. So we have an across variable source, and so we're specifying v in. If we want to find f in, it depends on the system, right? And so in order to find the relationship between v in, which is our input, and we're going to choose our output to be f in, which is totally valid. We've never done that before, I don't think. In an example, we've never chosen the other source variable to be the output, but it can be. There's no reason it can't be. So it can be our output. So f in is related to v in with this transfer function y of s. Okay? We define y of s to be the input admittance. Okay? So the system is going to determine how this across variable source becomes a through variable. So let's say we make this very concrete. Let's say that you have a voltage source, okay? And you connect it up to a system that is just a resistor, okay? That voltage source is going to be, say it's a 5-volt source. It's going to be 5 volts, no matter what you connect it to, if it's an ideal source, right? So you connect it to a resistor, and how much current that source provides, which is the through variable, like f in here, depends on that system. So the resistance of the resistor in this case, right? The current's going to be the voltage source, so 5 volts, divided by the resistance. And then, so your transfer function in that case would be, y of s would just be 1 over r. Pretty cool, right? Not so bad. And so we call y the input admittance. So, similarly, for an input that is a through variable input, notice I'm using this EDST multiplying on it. I'm doing that because we're just restricting ourselves to the one class that we've learned transfer functions for at this point. Turns out this is also more general than that, but it's mathematically easier, and the chapter does explain a little bit of the details of this. The resulting particular solution for the across variable v in e to the st is defined by the transfer function z of s. So we write that expression v in of s equals z of s times f in of s. So this is the case of a through variable source. And a through variable source is going to specify f in. We're going to go through this transfer function, z of s. We're going to get v in. So that's just like if you had a current source, which you guys aren't as familiar with, but you can specify current source. The current source going into a system, say that system is just a resistor, okay? Then the voltage across that resistor is going to be determined by what the current is, right? So if you have a current source going into a system that is just a resistor, okay, then that current is going to be specified. It's going to flow whatever current through that resistor that you specify. The voltage across that resistor is going to depend on what the resistance is, right? And this voltage is going to be I times R, right? So that's that. So it's like it's not super complicated when you think about concrete things, but when we make it very general, sometimes it gets like we get a little intimidated by the generality. But we need not be intimidated. Okay. So we define Z of S, and I want to see if anybody can have a premonition about what it is going to be as the, what are we going to call it? The inputs, what? Does this equation look familiar? If this is voltage and current, so V is voltage, F is current. You're getting, I mean, thinking along the right lines. So if you have voltage and current, what is this? Yeah, so it's Ohm's law, right? And so, but when we did the generalized Ohm's law, remember generalized Ohm's law? It was that the voltage is equal to the current times not the resistance, but more generally, the impedance. Aha! Input impedance. And so we now have the impedance defined. So if you look back at mechatronics, you're going to find that this is like almost identical to what we did in the context of electronic systems only. But now we're doing it more generally. Any through variable, any across variable, any energy domain. Okay? And this relationship will be apparent if you look at those two expressions. It is apparent that if you know the impedance, you know the admittance, and vice versa. How are they related to each other from looking at these two expressions?
Well, if you divide the theory F and by Vn, you get the inverse of Z of S. So that's just the inverse of Z of S.
Yeah, so it's essentially just a reciprocal of each other, right? They're just reciprocal. So y of s is equal to 1 over z of s, and vice versa. Z of s is equal to 1 over y of s. So it's just a reciprocal relationship. And so if you know one, you know the other. And that's pretty straightforward. Okay, whew! Got that done. That's practically the whole chapter. I know, impressive. So, impedance of ideal passive elements. So if our system is just a single passive element, then it's pretty easy to compute it, and we're going to do that for these simple cases. So the impedance and admittance of a single ideal one-port element is defined by its elemental equation. Shades of Ohm, generalized Ohm's law here again. We did essentially this in, way back in mechatronics. So generalized capacitors. So the elemental equation for a capacitor is that C dVc dt, dVc dt is equal to IC, right? I just rearranged. Usually I put the 1 over C over here. I shouldn't use I should use F, the generalized through variable, right? but it's I for an electrical system. Okay, so this gives us, we can write, so cool thing, if we write the transfer function, so the elemental equation, so this is sort of like an aha thing here. The elemental equation for any given element is a differential equation if it has a derivative in it. So this is a derivative. This is a differential equation. An input-output differential equation, you could say. It relates VC and FC. So if we consider FC to be the input and VC to be the output, we could write this as a differential, or this differential equation as a transfer function. By wherever we see the time derivative, we put an S, right? And that's essentially all we have to do. So transfer function can be found by just plugging in, so C, time derivative, S, then VC, and then now instead of just being VC of t, we'll say this is VC of S, okay? VC of S equals FC of S. So if we were to write that in terms of an impedance and an admittance, we would do this. So Z of S equals, so it's the across variable of S divided by the through variable of S. Thank you for getting the door. That is, so back up here, Z, if we want to solve for Z, it's going to be V over F, right? So we solve for Z here, it's V over F. What is V over F for a generalized capacitor? One over CS. Excellent. And what does that mean the admittance is of a generalized capacitor? Which is always equal to FC of S over VC of S, just CS. So that's pretty straightforward. So the impedance and the admittance are easy enough to find for a generalized capacitor. I would recommend just knowing this, just memorizing. I recommend memorizing the impedance ones and not the admittance ones. I think in terms of impedance more easily than admittance. But if you remember the impedance of a capacitor, an inductor, and a resistor, you're in pretty good shape. You don't have to derive it every time. But you could always go back to the elemental equation and derive it. You know the impedance is just the across variable over the through variable, and you could derive what it is. It's just a transfer function. Similarly, with an inductor, the elemental equation is L dFL dt equals VL, and so the transfer function can be found from using the rewriting this as a this differential equation as a transfer function, or in terms of the S parameter. We have LS FL of S equals VL of S, and what does that mean the impedance is? So the impedance is always V over F, right? Crossover through. And so V over F is just LS, I heard it. And what is the admittance? Yeah, just the reciprocal. FL of S over VL of S equals 1 over LS. Okay. And then the shocker generalized resistors, elemental equation is that VR is equal to R FR, right? So Ohm's law, but like more general for any type of D-type element. So if we were to take that and try to find a transfer function for between V and R, what would we write? Yeah, so I mean VR over FR is just equal to R, right? And so that means that what is our impedance? Just R. And what is our admittance? 1 over R. Okay. So pretty straightforward for those. And we have the impedance and admittance of each of these. Okay. Now would be a good time for me to draw your attention to a resource on the website. I don't know why I said it like that, but I did. So if you go to the resources, and you go here, and then you go to impedance notes. Bum, bum, bum. So this is a little handout made by a professor at UW, who I learned a lot of what I know from him, Joe Garbini. And this has the mechanical, rotational, electrical, fluid, and thermal, which we have a full stack now. We can do all of those systems. It lists what their cross variable is, what their through variable is, what their admittance and impedance is as far as definition goes. And then for the A-type, D-type, and T-type, so mass, spring, damper, for damper spring for mechanical, rotational, it's this. For an electrical system, it's this, fluid, thermal. So you can just look up in the table, or you can just remember the elemental equation and derive it from that. Either one is totally fine. I kind of recommend printing this off for an exam, so that you can just look off this for what the impedance of any given element is. Okay, and then this next part, next set of notes, 16 is essentially summarized in this next little bit of the handout. It's a nice little handout. Okay, I'm going to switch over to another lecture though before I begin. Although it won't let me. Come on. It's because it's supposed to be on this bar here, and it's like unavailable because I have too many things.